Welcome back to Part 9 of Alpha Found. With this video we begin new material. There are many thoughts that I would like to express all at once so that questions and objections can be answered before they're asked. Since this is not possible, the answers will have to come in their own time. The mathematics will not get beyond elementary statistics. However, from this point forward, I'm assuming the viewer can keep up without much trouble. This video has insights that to my knowledge are new and other insights that are old, but I'll derive them carefully anyway. The old insights relate to the fact that correlation and Sharpe ratios would seem to be related. The new insights are that beta and correlation affect one another in a structured way, which then affects what is expected in the relationship between alphas and Sharpe ratios. A simple method of portfolio construction is used throughout the videos that can be analyzed algebraically by standard ordinary least squares estimation metrics and Sharpe ratios without regard to data. Data is examined in this video and in some later videos to show how it is consistent with the algebraic analysis. For our purposes, portfolio construction occurs by ranking all stocks in a capitalization-weighted index by ordinary least squares estimates of CAPM beta with alpha from highest to lowest, and using that index as a standard for comparison. The index is divided into two portfolios, each with 50% of the market capitalization, one called the high CAPM beta portfolio and the other one called the low CAPM beta portfolio. The two portfolios are mutually exclusive and exhaustive of the index. Portfolio weights are rebalanced each time period. As I said previously, the prime notation is used whenever a statistic or parameter has its ordinary meaning in the context of CAPM. Statistics or parameters without the prime mark are defined when they are used for the first time. Here I will just point out the pattern. Statistics and parameters with the subscript h refer to the relevant measure for the high CAPM beta portfolio, and the subscript L refers to the relevant measure for the low CAPM beta portfolio. The subscript M refers to the market or index portfolio, which is the equal weight sum of the high and low CAPM beta portfolios. Take a moment to look through the notation to see how it's used. The phrase generally rising market is any series of time periods where both the arithmetic and geometric mean returns are positive. A generally flat market occurs when the arithmetic mean return is positive while the geometric mean return is negative, and a generally falling market is a series of time periods where both the arithmetic and geometric mean returns are negative. By construction, an OLS regression of the two portfolios described above will have estimated CAPM betas of their two portfolios summing to 2 with an average of 1. I should mention that portfolios constructed in this way will give results that are heavily biased or less than rigorous. This is one of the problems with using OLS to estimate CAPM beta for a portfolio consisting of a large portion of an index. The new model, when we get to it, will not have this problem. Also, the regression residuals for each observation of the two portfolios are equal in magnitude but opposite in sign. Consequently, their residual variances, idiosyncratic risks, are identical. So for simplicity, it is referred to as sigma hat prime sub epsilon squared for both portfolios. Their realized alphas, if they exist, are equal in magnitude, opposite in sign, and sum to 0, as shown here. Under this construction, in the standard CAPM framework, including alpha, the expected alpha of the low CAPM beta portfolio is the expected alpha of the high CAPM beta portfolio, each being 0. Also, assuming complete diversification or efficiency of the two portfolios, the expected Sharpe ratio of the low CAPM beta portfolio, the high CAPM beta portfolio, and the market portfolio is the same. I should mention that some might say if the two portfolios were completely diversified, there would be no residuals. Ex ante that may be true, but given random variation, it would not be true ex post. As a consequence, it is impossible for 9.4 and 9.5 to be realized at the same time. See the discussion later in this video and in later videos for details. Each of 9.4 and 9.5 is a possible interpretation of what it means for markets to be efficient. The expectations found in 9.4 and 9.5 are not realized in actual market data. Instead, results from ex post portfolios so constructed usually have the following pattern. In light of the expectations of 9.4 and 9.5, the commonly realized statistical relationships found in 9.6 and 9.7 will serve as the definition of the volatility effect. To the extent that 9.6 and 9.7 can be expressed as mathematical expectations ex ante, the volatility effect is resolved. With the relationships in 9.1 through 9.3, three interesting observations follow. The first observation is that with equal idiosyncratic risk for each portfolio, the correlation of the high CAPM beta portfolio is necessarily higher than the correlation of the low CAPM beta portfolio. Let me prove this. Assuming that in the usual case, correlation is between 0 and 1, then from any textbook on elementary statistics, correlation is equal to the square root of r squared, which equals the square root of SSM over SST. Moving the right-hand term into the context of CAPM with these substitutions gives this messy term on the left. The alpha terms on the left-hand side cancel and so do not appear on the right-hand side. Then, in the next step, beta prime is pulled out of the parentheses and gets squared in the process. The betas cancel out in the right-hand term. In the denominator of 9.9, if beta prime is larger than 1, the contribution of the residuals to the denominator is diminished, therefore increasing correlation. If beta prime is less than 1, the contribution of the residuals to the denominator is magnified, therefore reducing correlation. Consequently, when an index is divided equally between two mutually exclusive and exhaustive portfolios, as long as there are regression residuals, the one with the lower CAPM beta will always have the lower correlation, which means observation 1 is always true. If an index is divided into more than two portfolios, for example deciles, the regression residuals will no longer be equal in magnitude and correlation will vary more freely. However, there is a general tendency for correlation to follow CAPM beta when an index is broken into a larger number of portfolios, but it shows up in an unexpected way. If we look at the data from The Volatility Effect, Lower Risk Without Lower Return by David Blitz and Pim van Vliet, they report CAPM betas ranked by decile along with the standard deviation of each CAPM beta decile and the market standard deviation. From this, the correlation each decile has with the market can be easily derived. Blitz and Van Vliet provide information on markets in the US, Japan, and Europe over the time period 1986 through 2006. If we start with the formula for CAPM beta, by moving terms around, the correlations for each beta decile can be calculated using this formula. Here is the result of the correlation calculation. It's in the fourth line of each of three statistical groupings found in Table 9.1. At first glance, the correlation data may not show much, but on a closer look, if we examine the correlation of each decile and its corresponding symmetric decile, in each case, the higher beta decile has a higher correlation than the lower beta decile, as seen here in Table 9.2. You may have to stop the video from time to time to review the tables. In total, there are 15 pairs of matched deciles, and each of 15 times the higher beta decile has a higher correlation than the symmetric lower beta decile. Using the same procedure on Black, Jensen, and Scholes, Table 9.3 shows there are 4 time periods with 10 deciles plus the aggregate time period. As shown in Table 9.4, in 4 of the 5 time periods, there is the same pattern of higher correlation with the higher beta decile when matched against the symmetric lowered beta decile. In 1 time period, 4 of 5 matched deciles have the same pattern. Since the relationship has been proved to be necessarily true when an index is divided into 2 halves, it seems that for deciles the pattern is far too consistent to be just a happy coincidence. This issue is pursued further in videos 30 and 31. A few minutes ago, I said there were 3 observations that flow directly from equations 9.1 through 9.3. The relationship between correlations was the first. The second observation is that the Sharpe ratios of any individual security or portfolio with 0 alpha equals the correlation multiplied by the market Sharpe ratio. Although observation number 2 is not new, we should prove it anyway. In the process of proving observation number 2, most of observation 3 will also be proved. Proof. Here is the formula for the Sharpe ratio. Beginning with 9.8, if the standard deviation of the market is greater than 0, and with a generally rising market, the difference in correlations can be multiplied by the market Sharpe ratio to get the following. Distributing the denominator gives and then multiplying each piece in the parentheses by 1 in the form of portfolio standard deviation divided by portfolio standard deviation. Since the formula for CAPM beta is in the numerator of each term on the right, then CAPM beta can replace the numerator of each term. Then multiply through by the average excess return of the market, and then add and subtract the risk-free rate in the numerator of each term. If we assume the alphas are 0, then the Sharpe ratio of the high CAPM beta portfolio is higher than the Sharpe ratio of the low CAPM beta portfolio. By inspection, you will see that this pattern reverses if there is a generally falling market. Recognizing that the two portfolios have different correlations, the third important observation follows. The market portfolio, having a correlation of 1 with itself, will necessarily have a higher correlation than the high CAPM beta portfolio, which will have a higher correlation than the low CAPM beta portfolio. Therefore, in a context with idiosyncratic risk, if the realized alphas are 0, the relationship between the Sharpe ratios is necessarily as shown on the screen. This is contrary to the observed volatility effect. The conclusion is, in a generally rising market with idiosyncratic risk, if the Sharpe ratios of the high and low CAPM beta portfolios are equal, the alphas are not 0. Putting it together leads to one of three possibilities. If the alphas are 0, then the Sharpe ratio of the market is greater than the Sharpe ratio of the high CAPM beta portfolio, which is greater than the Sharpe ratio of the low CAPM beta portfolio. If the alpha of the low CAPM beta portfolio is greater than 0, which is greater than the alpha of the high CAPM beta portfolio, either the Sharpe ratio of the market is greater than the Sharpe ratio of the high CAPM beta portfolio, which is equal to the Sharpe ratio of the low CAPM beta portfolio, or the Sharpe ratio of the low CAPM beta portfolio is greater than the Sharpe ratio of the market, which is greater than the Sharpe ratio of the high CAPM beta portfolio. In every study I could locate, a decile variant of 9.18 held in market data. As a preview of coming attractions, the various expectations in 9.16 through 9.18 can be derived mathematically from assumptions about market dynamics without reference to financial, economic, or behavioral issues, although such issues inform market dynamics. When that mathematical derivation is complete, then to that extent the volatility effect is resolved. That is, 9.16 through 9.18 and several other possibilities will eventually be shown to be mathematical expectations depending on conditions. We're not quite ready for that, but we're getting close. In this video, it has been shown that correlation is connected to CAPM beta, and that under CAPM expectations with ordinary random variation in the data, the Sharpe ratio of the low CAPM beta portfolio is expected to be lower than the Sharpe ratio of both the market and the high CAPM beta portfolio. This expectation is not met in real data, and it's not met in a systematic way. This difference between expectation and reality has come to be called the volatility effect. The next video visits some data. By using the two portfolio index construction method presented in this video, we will see that the positive alpha of low CAPM beta portfolios is much more prevalent than previously thought.